Okay, so we are going to be doing test 2 soon, and I know some people were wanting to come to office hours and they were already all booked up, so I was like, okay, maybe I could do a little bit of a brief review for what we'll be doing for test 2. You got the multiple choice part, which is TYK 4, 5, and 6. The more applied part, we're going to be doing the actual statistical analyses. We're going to have a z-test, correlation, and a simple regression. And I created some practice problems. If you want to go through them, you can. There's the save file, there's the Excel file. The first one, this is the z-test. We have a group of incoming graduate students. Their GRE scores, we're going to compare them to the national average. We don't know if they're going to be higher or lower, which means it's going to be a two-tailed test. Sample size 25, standard deviation is 50. Our mean for this sample is 725 and the national mean is 600. Let's assume it's a two-tailed test with an alpha of 0.05. What's the critical value? 1.96. We've been over that a lot. 1.9 plus or minus, when you're doing a two-tail, plus or minus 1.96. So if we go above that or below negative 1.96, we're going to have a significant finding. You could use a calculator. I have my Google Sheets, and I've already put it in. So our sample 725, population 600, standard deviation is 50, our N is 25, doing the 0.05, and the two-tail critical value is at 1.96. We get a Z-score of 12.50, so it's very significant. So we'll go back, and so yeah, what is our value for Z? We can see it right there, 12.50. Do we have a significant finding? Yes. If we go over 1.96, which we went well over 1.96, so it is significant. Okay, on the next one, you open up that Excel file, you do a correlation matrix for A through H, and all you do is go analyze, correlate, bivariate, and then move all of those over. Click OK. And then all we're looking for is the significant pairings. You can look at the ones with the asterisks. You could actually look at the p-values. We're looking for p less than 0.05. But if you just look at the asterisks, that'll work too. So this one's, our R is 0.67 and our P is 0.04. The 3.5 would round to a 4. Line those up, E and B. So E and B are, or B and E, either way, are significant, and B and F are significant pairings. And I believe that is all. If we wanted to, we could do that also in that Google Sheets. Just copy that over, go here to the correlation matrix, plug those numbers in. This part is our Pearson's R right up there. And then this is our p-value. You don't have the asterisks, but all you're looking for is a number that is less than 0.05. And we see it the same thing as it was before. So B and E is 0.035, and then B to F is less than 0.01. So those are the two pairings that we're looking for, E and B, B and F. Okay, on this one, is there correlation between temperature and ice cream sales? Conduct the appropriate analysis. SPSS. So temperature and ice cream sales. Analyze, correlate, bivariate. You'll reset it. Move that temp and ICS over. Click OK. We get our output right there. The Pearson's correlation, the R, if you scroll over a little bit, 0.93, and it is significant. Our SIG, p-value, less than 0.001. While I'm here, I'm going to grab that data. So I do Control-C, and then I can go back over here to this, and I can put in, if we go to the correlations, and then right here I can put Control-V. And yeah, right there, same numbers. Correlations 0.93. Our degrees of freedom is 12 because it's n minus 2 for a correlation. So our n was 14. Degrees of freedom would be 12. And our p-value, it's less than 0.001. And that's how you want to write it up. We're either going to be doing less than whatever like the more rare test is. So if you meet 0.05, that's what you write. If you get less than 0.01, that's what you write. And if you get less than 0.001, that's the proper way to write it up. Okay, so yeah. 14 was the N, which means our degrees of freedom are 12. Our R was a 0.93, and then that P was less than 0.001. Do grades predict absences? This is going to be a regression of grades and absences. Analyze, regression, linear, and then we'll put grades as our dependent variable, or DV, and then absences is our independent / predictor variable. Put that there, click OK. The numbers that we need from this, we need our R square, how much variance can be explained by the absences, 0.57 or 57%. From our ANOVA table, we're going to need the degrees of freedom, the 1 and the 59. We'll need our F value, the 79, and we'll need our P value, less than 0.001. Copy this if you want to do it in the sheets. And I will post in the test. You can just open up the Excel sheet. If you wanted to actually use Excel, you could post these over or paste them over. Simple regression, we'll enter in our values. You want to double check when you're doing this though. See, so all this is not actually part of our data set. So you do have to remove that part. Delete cells, shift up, that clears that out. Same numbers as what we had in SPSS. So 0.57, 57%, 1, 59, our F, 79, and then you'll see our P is less than 0.001. Yeah, you just enter those numbers in. Okay. Two other ones. Does marketing predict sales? It's the exact same thing. So analyze regression, linear, reset it, move the international sales to the dependent, the marketing to the independent. Click OK. And there we go. Model summary, our ANOVA table, and we'll talk about coefficients later on. I do want to copy this over to show you what you need to do if you are going to use the sheets. Go here, go to simple regression, our DV first, then our IV. And so yeah, our data set this time is much bigger than the previous one. So what you do need to do is you need to grab all these and drag those down to make it even with the data set down there, and then we should be good to go. R squared, just like SPSS, 0.28, R degrees of freedom, 1, 131, F, 51, P less than 0.001. Go back over here, and so you'll see the answers there. 1, 131, 51, 0.001, 0.28. So my suggestion would be to do those practice problems first, and then if you made mistakes, watch this video and you should be able to match them up. The final part, let me do it in preview mode so you can see how I would do it. This is what it would look like on the test. Fill out the table below, ANOVA table for simple regression that had 16 participants. So there's two things that are key here, 16 participants and then how many predictors we have. Predictors, you ignore the constant, absences. So we only have one predictor. For correlation, degrees of freedom, n-2. For a regression, it's n-1 because we're really just looking at the y variable when we do this. So our total degrees of freedom are going to be n-1. So we have 16, that'd be a 15. If we only have one predictor, our regression model is only going to have one. And then whatever's left over, the residual, so 15 minus 1, that goes there. We kind of divide them this way. So 200 divided by 1, you get 200. 60 divided by 14, we get a 4.29. Then for our F value, it's those divided by each other. So 200 divided by the 4.29 equals 46.62. Then what we would do is go look up the F value, and the chart only goes, it does 0.05 and it does 0.01. And you would look to see, does 46 exceed whatever the critical F value is? I just know because I've done it for so long, it's like 46 is pretty big. And if we have an N of 16, that is going to be less than 0.001. But the chart only goes to 0.01. So that's the correct answer. You could put that because your chart doesn't go to 0.001. If you put that, either answer would be acceptable. Okay, I hope that helps. And yeah, I think if you go through this, it'd be just kind of to finish up. It's like if you've done the homeworks, if you've done the quizzes, and if you go through these, you should be good to go for test 2. All right, thank you for listening.